Hello and welcome to Algebra. Today we're going to look at a new section. We're going to look at exponential growth and decay. We're going to continue looking at our exponential growth or our exponential models of functions, but here we're going to look at exponential growth and exponential decay. Now what this means, growth and decay, is when we're talking about an initial amount and a growth factor, the growth factor and decay factor are very, very similar. You think of any number bigger than 1, say 3. 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, times 3 is 243, and so on. It's getting bigger and bigger. That's because the number is bigger than 1. If you look at any number smaller than 1, and let me say between 0 and 1, positive between 0 and 1, say 1/2. 1/2 times a half is 1/4, times a half is an eighth, times a half is a 16th, times a half is a 32nd, and so on and so forth. So it's getting progressively smaller and smaller, and that's the difference between exponential growth and exponential decay. Now, the initial amount is right in front here, so if you start with, say, 20 goldfish, that would be your initial amount. And of course, if you have more and more goldfish, then that'd be exponential growth. Less and less goldfish, that would be exponential decay. And the way that you can tell is by looking at this factor here, the base of that exponent, of that power. If that is bigger than 1, let's say that is 1 and 2/10, well, how much bigger than 1 is it? Well, it's 2/10, which is 20 hundredths, which is 20%. So this would be exponential growth, and the growth factor would be 20%, or excuse me, the growth factor would be 1 and 2/10, but it would be increasing at a rate of 20%. If you had, say, 4/5 as the base, well, your decay factor is 4/5. How much less than 1 is it? It's 1/5. 1/5 is 2/10, which is 20%. So your rate of decay is 20%. Your decay factor would be either 8/10 or 4/5, however you want to put that. Okay, so we just want to identify the initial amount A and the growth factor B in each exponential function. Well, here is your initial amount. So the initial amount is 14, and let's go ahead and make that a complete sentence. So the initial amount is 14. Now this is growth because this is bigger than 1, this base. And how much bigger than 1 is it? Well, it's 1. 2 minus 1 is 1. 1 as a percentage is 100%. So your rate of increase is 100%, but the growth factor is 2. So the growth factor is 2. If they had asked for the rate of increase, it would be 100%, because that's how much bigger. It's 1 bigger than 1. 1 plus 1, 2. And so that would be a rate of 100%. Okay, a little bit different situation here. A population of 100 frogs increases at an annual rate of 22%. How many frogs will there be in 5 years? So we're going to start off y equals a times b to the x. Our initial amount is 100 frogs. Annual rate of 22%. So how much bigger than 1 is it? It is 22% bigger than 1. I just converted to a decimal, added 1 to it, and that is to the x power. So we're going to go ahead and evaluate that. Just plug in 5. So y equals, just run this through a calculator, it's going to be about 270 frogs. Now write an expression to represent the equivalent monthly population increase. Well, to do that, we're going to take this part here, and we're just going to figure out for the month. So we're focused on monthly population increase. Well, 122% or 1 and 22 hundredths to the x, that's in terms of years. We have to think in terms of months. There are 12 months in a year. So what we're going to do is we're going to make this a fraction 12 over 12. And then we're going to sort of do an inside-outside 1 and 22 hundredths to the 1/12th power. Of course, we would multiply these two numbers. 12 times 1/12 would be 1, and so it would come out to be x. We're just changing it slightly. Now you would need a calculator to evaluate this, to simplify that. You could think what number times itself 12 times is 1 and 22 hundredths. That's going to take quite a while. Instead we could just go through on a calculator, raise it to the 1/12th power, and that's going to give us 1 and 2 hundredths. Instead of saying 12x, we could just say to the m for month, and so that would be the second part. So there would be two parts to our answer. We would say there are, or we should say there will be, look, how many frogs will there be in 5 years? There will be about 270 frogs. Run expression to represent the equivalent monthly population increase rate, 1 and 2 hundredths to the m. And that's it. So that introduces us to exponential growth and decay.